Great. It's such a pleasure to be here, and I'm looking forward to the workshop tremendously. I was asked to give a review, but I have to confess this is going to be a very biased review, given that all the other players are actually giving the next few talks. So what I want to focus on is the center of the galaxy and the work that's been possible to do there because of its proximity. As the closest galactic nuclei, we have an unusually good view of this center of a galaxy. And in particular, it's the only galaxy in which it's possible to make measurements of stellar orbits. And as a result, there's a few interesting things that can be pursued with stellar orbits. So from the physics side, the initial question that set off all these experiments was to establish the existence of a supermassive black hole, which of course I think we've come up with convincing evidence. And today what drives the physics side of this is to explore what the complete theory of gravity is. On the astrophysics side, we would like to understand how black holes grow and shape their host galaxy. Because of course today we have this picture where there's a correlation between the mass of the black hole and the mass of the central part of the galaxy, the bulge. And all of this has become possible thanks to the tremendous progress that's been made in high-resolution imaging over the last 20 years. So 20 years ago, we got the first diffraction-limited images, which improved the angular resolution by a factor of 20. And over the course of the 20 years, there's been tremendous progress in how this is possible. And we'll hear from Stefan and Frank how they are now making the next step with gravity. But I do want to emphasize the technology pieces. The fact that we've increased the sensitivity of infrared detectors, the fact that the mirror sizes have increased, and the fact that it's now possible to make high angular resolution images through adaptive optics are the key. All of this started with Speckle imaging, which gave us the first glimpse of the center of the galaxy. So this is a technique where we take very short exposures and freeze the distorting effects of the Earth's atmosphere and allows us to discover the presence of stars at the center of the galaxy. And over the last, the first 10 years, this enabled us to see the motion of these stars. And it's worth remembering, or at least I like to point out at this point, that at the beginning of these projects, no one believed that this was possible. The first time that we proposed to make these measurements, it was turned down because people did not believe that the imaging technique would work. And even if it did, we wouldn't see stars. And even if we saw the stars, we wouldn't see them move. So I still, 20 years later, love seeing this animation. There's nothing PR about this. This is actually the original raw images, or just stacked, and showing you one year after another. So you don't need a computer to tell you that they're moving very fast. And of course, adaptive optics has changed our ability to see the center of the galaxy tremendously. So we've gone from a mode where we take a lot of images. So in a sense, I like to call this was the hardware simple. The technology was quite inexpensive compared to what we do today, which is millions of dollars. This was a few tens of K to build the first Speckle imaging capability. Now, but adaptive optics is a hardware complicated, and while we used to say software simple, in contrast to the Speckle imaging, it is also software complicated as well. So this allows us to real-time correct for the distorting effects of the Earth's atmosphere. This animation now shows the central arcsecond. On the left, is what we were looking at before, which was the first decade of Speckle imaging. And on the right is the adaptive optics images. So this shows you the improvement in the imaging capability. And this improvement allows us to position the stars much more precisely than we could before. So you get much better astrometry. But also, for the first time, you can take images at different wavelengths, and you can take spectra, which gives us both the third dimension of motion, the motion along our line of sight, which is important for the dynamics, and also reveals the kinds of stars that we're looking at. And of course, there's been many surprises on this front. Today, although you'll hear from Tuan in a few days, that most of the work that's been done here has been fairly low spectral resolution. So in fact, the identification of the stars is quite simple. One characterizes them as either young or old without too much distinction between them. So there's a tremendous amount of work to be done in terms of the follow-up work on the spectroscopy. With 20 years of data, it's also worth doing a lot of work on improving the methodology. And this is work that Rainer Schottel has done quite a bit of work with us on, which is just improving what you can extract from the first 10 years of data. So let's look at where we are today with the work on the central potential. This is an animation now that zooms in further than the central arc second. Now this is a central half arc second by half arc second, so you're looking at a quarter of the real estate. And this animation has gotten more complicated over time because the technology has evolved over time. So once an object is picked up by images, it's trailed by a dashed line. So you see stars appearing, not because they're variable, but rather because the depth of your imaging capability has gotten much deeper. And then you see stars trailed by a solid line once it becomes possible to take a spectrum of the object. So you now have the third dimension of motion. So you can see, you can probably tell from this animation which stars are the most important from the point of view of understanding the central potential. And that is primarily SO2 because it now has complete orbital phase coverage in both the astrometric and the spectroscopic domain. The spectroscopy, of course, was just started later on. So SO2 is, so to speak, the star of this show. There is a runner. It has an orbital period of 16 years. And these plots now show you the real data rather than just the animated version. So on the left, we have the astrometry, and on the right, we have the radial velocities. So you can see the closure of the orbit. And you can also tell that another issue that we have to worry a tremendous amount about is source confusion. So when there's an underlying source, the points are unfilled. And in the work that we do, we currently ignore these points. The closest approach is a little bit of painful point to throw out. And so there's a lot of work that's been done by Stefan and our group to try to figure out how to recover those points fairly. You'll also notice that the orbits don't appear to close in this plot. And that's because we're plotting it in the reference frame where we've attempted to put Sag star, the emissive source associated with the black hole, at the origin and at rest, but that is an imperfect process. So if you ask me what keeps me up at night with respect to this project, it is actually the reference frame, and I'll come back to that in a moment. On the right is the radial velocities, and it's worth noting that the units go from 4,000 kilometers per second to minus 2,000 kilometers per second. This plot shows you that at closest approach, there's a tremendous change in the radial velocities. And you might ask why we didn't take more measurements in these epochs, and that's simply because we didn't know the orbit well enough. So hindsight is always 20/20. So today we understand that 2018 is a particularly important year for understanding these orbits for reasons that I'll get to in a moment. All right, so this is our current estimate using those two stars. It matters which stars you use. So it's a trade-off between orbital phase coverage and the price you pay for adding more stars, which include for which you incur biases. All these faint stars suffer. Many of the other stars are quite faint and have poor phase coverage. So you have to worry about the systematic errors from source confusion, the less phase coverage you have. So our current mass is 4.2 million solar masses, and our current distance is 8.1 kiloparsecs. Okay, now this has obviously provided us with the best evidence to date for the existence of a supermassive black hole. This is a rather old plot, but I'm going to show it anyway, which shows the black hole, the dark matter density is a function of mass. And the center of the galaxy has now become the most extreme case where the inferred dark matter density is 6 times 10 to the 15th solar masses per cubic parsec. And this is an increase in the dark matter density by a factor of 10 million. So you can now rule out alternative possibilities for the central dark mass, including clusters of dark objects, and then the ideas that the particle physicists have put out, including the idea of a fermion-Wall well, there's in the region that, so we know from the orbit that we've confined 4 million solar masses within inside the closest approach of SO2, which is 100 AU. So that's how you get the mass density. Right. And in that region, there's very little light that is emitted. So that's how we come to the statement that it's dark matter. Oh, yeah, sorry. Dark mass, dark mat. Yes, sorry. Dark mass. Tell me what the right word is. It dark mass? It's dark mass. Yeah. So there's a lot of mass without a lot of light. So the dark mass that we see at the center of the galaxy has a density of 6 times 10 to the 15th. Yeah, it's just the black hole. Yeah. Yes, and I'll get to that in a second. So SO2 allows us to probe both the matter distribution more carefully, as well as the gravitational physics as well. So SO2 offers us the opportunity to study gravity, and as Jeremy's pointing out, mass as well. So there's there's just a few tests of gravity. Of course, the most exciting recent tests are from LIGO. But these short period stars offer an opportunity to probe gravity in a different regime. So we'd like to use these stars. Let me actually just use this plot instead. This is a little animation that conceptually shows the different tests of gravity, as well as probes of dark matter that one might be able to do. So the first test that it becomes accessible to all the groups that are involved in this work is a probe of gravity by looking at how light is affected by the curvature of space-time. In other words, the gravitational redshift. And that becomes accessible as SO2 goes through its next closest approach. And this happens in 2018. And as I'll show you, actually, let me just skip forward to show you this. 2018 is important not only because it goes through closest approach or is a what I call a turning point in imaging space, but it also has 2 turning points in the spectroscopic space. In other words, the radial velocity also goes through a maximum and a minimum. So you have 3 out of the 4 turning points all happening in 2018. So while I think we were all very worried about whether or not this would actually happen during the summer months for many, many years, so the time of closest approach is key. So this shows you on the left the difference between the relativistic orbit and the classical orbit. So at closest approach, the difference along our line of sight is 200 kilometers per second. So at first blush, you might think, well, this should be an easy measurement, given that the uncertainties in the radial velocities are about 10 kilometers per second. But you have to know your classical orbit well enough. So that actually is your dominant source of error, which is how well do you know the classical elements. All the information is going to happen in the course of 2018. So all the groups have all submitted their telescope time proposals. More, I don't know, but what we were most worried about was the timing. So the shaded area represents roughly the time over which the center of the galaxy is observable. In other words, there's only a fraction of the year that you can see the center of the galaxy. And the reassuring thing that we have found is that the closest approach and the turning points will all happen within this season. Yes. I know. Well, I knew. Yeah. Okay. So currently, and this is where we all know that while statistical errors are the easiest to report and determine, systematic errors are the things that are actually hardest to establish and usually dominate. So May 9th is our current estimate of closest approach. Yep. But it does, and you can say plus or minus just a few days statistically, although systematic-wise, I'd say there is at least a week flexure in there. And so in fact, the earliest turning measurements at the beginning of the season, the reason those are so important is just to establish your true timing. So everyone's going to hope that the telescope, the observatories will be as flexible as possible. So we, at least at Keck, have really worked hard to see how much flexibility we can put in to a telescope that is really traditionally classically scheduled. So we're not quite a TOO program, and we're not quite cadence this year. We're somewhere in between. So everyone's hoping for lots of time. the other things that I would say keep me up at night in terms of whether or not this experiment is actually going to work are things like, is SO2 a binary? So binarity is becoming a hot topic, and it's certainly interesting for all sorts of reasons, especially dynamics. But if SO2 were to turn out to be a binary, that would be a problem for the measurement of the gravitational redshift. So we've taken all the past 10 years of radial velocity measurements that have been made by all the groups and put on an upper limit to the possibility of a companion. So you can rule out most kinds of companions, assuming that you know what massive stars look like as binary stars. And we've, given these limits, we've asked what kind of bias should be possible, or should you allow for the gravitational redshift. And if this is parameterizing the gravitational redshift from 0 to 1. So I think today, with even today alone, we can, I think, rest assured that this is not going to ruin the measurement. This is what Jerry was asking about, which is the precession of the periaps. So in principle, this should be possible. So the way I parameterized it is definitely from an observer's perspective, which is how much does the apoapse move in an orbit, after one orbit. And that's 0.8 milliarc seconds. Today, our precision is about 0.1 milliarc seconds. So again, for an individual measurement, that looks like or sounds like it's easy. What's hard is that you have to keep your reference frame stable over 20 years. So I'll come back to that in a second. Nonetheless, you can start to ask, given your ability to measure the precession of the periaps, you can both put limits, upper limits on the extended mass, which today are not astrophysically interesting, but this is an experiment where just time, it gets better with time. But you can start to ask, can we put interesting new limits on the concept of the fifth force? So the idea that there might be a fifth force that allows us to tie together general relativity and quantum mechanics. And what this shows is that the orbits do place an interesting new limit. And of course, this limit is just going to sink over time. And in particular, during 2018, because that's where there's a tremendous amount of power. Okay. So I wanted to just show you this. And I'm sure Stefan has a view on this as well. If you wanted to be skeptical, and of course this is, I think, super important, you should always ask us about our reference frame. So for the gravitational redshift, you can parameterize it, and it's not going to be a significant issue. For the precession of the periaps, though, this is a dominant issue. Because, of course, the non-closing orbits can equivalently be non-closing because of the reference frame. And the way we parameterize it today is just to allow the position of the dynamical mass to be not necessarily at 0, 0, and for its motion not necessarily to be at rest. But remember, the reference frame in all experiments have been constructed by definition for that to be true. So if your parameter that you've thrown into your model is not consistent with 0, 0, in either position space or velocity space, that's a signature of systematic errors somewhere in your system. So this is allowing for the highest level of systematic error. And I would say here that we're not using Sagittarius star, the emissive source yet to constrain the reference frame. So I think that could help us a tremendous amount. But this today is not doing that. And over time, these error bars shrink because your baseline is improving. So while in years past it was consistent with 0, 0, today it's moving away from that. So I'd say this is one of our biggest issues. Okay, so now let's look at the dynamics. The other things that can be done with this experiment or these measurements, these kinds of measurements, is to look at how the black hole interacts with its environment. And there's two aspects. One is the black hole accretion, which I will not focus on here, and the other is the dynamics, in other words, the stellar population. And from the stellar population, there's basically three big questions. One about the old stars, what is the structure of the cusp? And of course, this is a rapidly evolving story. Two, how did the young stars that we see there come to exist, and what is their dynamical structure? And 3, what is the role of binaries and the possibility of mergers? Okay, so this is a 3-dimensional animation. We've been looking at the 2-dimensional animation that's really zoomed in very, very tightly. This animation is a factor of 20 larger, so the scale is very different. And it's going to tilt your, the viewpoint so that we see some of the dynamical structures. The type of star is now coded. So remember, this is an interesting experiment because we actually have more information dynamically, astrometrically, than we do in terms of the radial velocity. And we cannot spectral type all the stars that we have good dynamics for. So if it's a known young star, it's color-coded as aqua, or blue-green. If it's known to be an old star, it's color-coded to be orange. And if it's a red emission line object, right now it's color-coded to be pink. So those were the things that we didn't think to make predictions for. So hopefully you'll notice a few things as this goes through. One is there's tons of young stars when the prediction was that there should be none. There's very few old stars where the prediction was that there should be lots. And of course, we didn't make predictions for the pink stars. And the pink stars, in my mind, are some of the most interesting new results from the center of the galaxy. So let's go through this. Some of these arguments are a little old. So the first paradox is, why do we have the young stars? The young stars, the paradox has been that given the gas densities that we see at the center of the galaxy, they're quite low compared to the required gas densities needed in order to get self-gravity to overcome the tidal forces. And this is not just a small discrepancy. This is orders of magnitude discrepancy. And so this is what's given rise to the concept of the paradox of youth. So the young stars, as you saw in that animation, show a dynamical structure. So as we pull back, you saw an agreement in the planes. This you have to be a little bit careful with because at larger radii, we only have small arcs. So you have what that animation doesn't show is your uncertainty in the orbital plane. But nonetheless, the direction of your orbits, the orbital normal, is actually the easiest thing to measure, the least biased thing, the first thing that falls out first from your orbital modeling. So on the plane of the sky, as seen from the black hole, which is what this graph is, if you plot the orbital normal vector, these look like noodles. So if you just ask, using all the tricks from galaxy clustering, those techniques of getting densities on the plane of the sky, you can get a density of orbital normal vectors, and you get one clear concentration, which suggests the presence of a stellar disk. The surface density of that stellar disk goes as 1/r squared. And an initial look, there's been a lot of debate about how many stars are actually in this disk. And so the last published thing said about 20%, but I'm actually going to tell you why this actually may be higher in a moment. And then the eccentricity in this disk also seemed a bit high. So these two things have been once you accept that there are young stars and you need some mechanism for forming them, and the mechanism that seems to be most in favor these days is the idea is that they formed out of a pre-existing stellar disk. And this comes from the fact that there's a very clear cutoff in the young stars. So the young stars really don't appear to be outside of the central 10 arcseconds. So you see these young stars in disk from 1 arcsecond out to 10 arcseconds. So 0.04 parsecs to about 0.5 parsec. So I'm going to return to that in a minute. So the unexpected result number 2 is the lack of old stars. So the old stars, one predicts that there should be a cusp at the center of the galaxy if there's a black hole. This has been a very important result for understanding the centers of galaxies. And here next, we want to look at what's observed. And here I really want to emphasize that that you're only seeing the brightest stars in these experiments. And you'll hear more about this from Rainer. So the old stars, and in particular the bright old stars, the ones where you can get dynamical information beyond just star counts. That's what I'm focusing on here. You can measure, you can do the genes modeling with 3-dimensional velocities, and you can ask what the 3-dimensional profile is, and that looks too shallow compared to the theoretical predictions. Now it's actually possible to go beyond velocities and actually to get accelerations. And accelerations on the plane of the sky is equivalent to getting z along the line of sight, and that's also consistently low. But the story here is that these is only the bright stars. The faint stars actually are much more consistent with the cusp. And here I'm just going to leave it to Reiner to go over that. And there's all sorts of possibilities, and I think there's some exciting results coming out that delve deeper into what these infrared surveys may be missing in terms of the cusp. So the unexpected result number 3 comes from the first spatially resolved, tidally interacting sources. So here I think the story is still in much flux, but I think what everybody can agree on is that there is evidence, or maybe, there's all the players in the room. So there has been good evidence that there is tidal interactions. In other words, as this object, which is on a very eccentric orbit, approaches the black hole, it develops an extended-like structure. And here I also want to emphasize that this object, known as G2, has been observed in 2 very different ways. It's been observed spectroscopically, where you're looking at the ionized gas. So it's presumably optically thin, externally heated measurements. These are probably the hardest measurements that have ever been reported from the center of the galaxy. This is a very, very faint line that is being extracted in the context of a lot of low surface brightness gas. So I cannot emphasize this enough, that this is a very, very hard measurement to make. The images, this is a very red object. So while this is the spectra are actually in the, at 2 microns, where you don't see the object in the continuum, although I know that's a topic of debate. We see them very clearly in the, at L-band, at 3 microns. It's one of the brightest objects that you see at 3 microns. This is a very easy measurement to make. And presumably what you're seeing is thermal emission from the dust. So just keep that in mind, that you're actually observing through these 2 different windows, different components of G2. Because I think this has caused a tremendous amount of confusion in the community when people talk about something being compact versus extended. Okay, so what's the debate? The debate is that this looks like it could be a gas cloud that would be tidally disrupted as it came through closest approach. And that was exciting because it is exciting no matter what your interpretation is, of the possibility of an object that is going to lose a tremendous amount of mass, and if you believe the tidal structure, it is losing a tremendous amount of mass at its closest approach. The closest approach of this object is very similar to the bright 2-micron sources that we see. SO2, SO38, all our favorite friends, they all have closest approaches that are roughly 100 AU. That's identical to this object. Okay, now, again, this is a very biased viewpoint, so you'll take it from these 2 guys to hear a different perspective. The fact that you see at 3 microns, this object has survived closest approach, and it has survived without changing its luminosity, suggests that G2 is not a simple gas cloud. Our interpretation of this has been that there is a star at the core of G2. And if you look at the luminosity of this object, it's consistent with being roughly 30 solar luminosities. If you interpret it as a black body, so the dust being an optically thick dust shell, would suggest that maybe at the core there's 2 solar mass stars. G2 is not unique. There's also G1. G1 was detected in also as a dust cloud. And this shows the orbital elements of these 2 objects. They're highly eccentric, and they're very degenerate. I mean, and again, remember, we're only getting closest approach. So you have very high eccentricity. The bottom down here is 0.88, and the top is 0.99. And the periods range from a few hundred years up to thousands of years are possible. G1 was actually, unlike G2, was actually slightly extended, although I have to be careful. It was extended when it was first detected. G1 is effectively 13 years ahead of G2. So it was discovered as it was just coming out of closest approach. So if we do this relative to the time of closest approach, G2 had a size at 3 microns. In other words, the dust shell was extended and then became compact. G2 is just reaching this point now. So I think it's interesting to ask whether or not you're going to see the dust shell emerge. Okay, and this also shows a plot that shows a position compared to its possible black body size as a function of time. So G2, this is an old plot, as you can see, is coming into closest approach, and this is G1. So you're getting sort of a very different view in terms of the interaction of the black hole. So our interpretation is that G2 may be a black hole-driven binary star merger, so taking the topic that Smadar has talked so much about, the idea of the Kozai-Lidov effect, so a 3-body interaction. And in this case, it would be the black hole being the third body interacting with the binary star. So this effect causes the little binary to oscillate in terms of both its eccentricity as well as its relative orbit. So from the point of view of this story, it's the eccentricity that's the most interesting. If you pump up the eccentricity high enough, you could possibly merge the object. If it merges, it looks like a protostar, and a protostar has the characteristics of the object that we see. They're very large, luminous, dust-embedded red objects. And it will stay in that state for 10 to the 5th, roughly 10 to the 5th years. So in other words, you're now talking about a scenario that has a time scale that's much longer than the orbital period of the object. What one might ask is, can binaries survive at the center of the galaxy? So with Smadar, we've looked at the survival rates of binaries. This is a fraction of binary stars given a population where you're assuming that everything starts as a binary as a function of time. The red are the mergers. So at the age of the young stars, the stars that are in the disk, which are Wolf-Rayet stars, you get roughly a little less than 20%, or roughly 10% of the population has merged. And you might ask, do binaries exist at the center of the galaxy? And the answer is yes. And from these measurements that people have been doing for the past 2 decades with imaging and spectra, that gives you a data set to probe binaries in all 3 ways, both through photometry, through astrometry, and radial velocities. Now, of course, the photometry has been the easiest way to probe first, and this is a classic example that was first reported by Thomas Ott of IRIS-16 Southwest. Okay, so these, I've become quite interested in the possibility of the important role of binaries at the center of the galaxy. If we think of G1 and G2 as early stage mergers, in other words, mergers that have not relaxed, then one might ask, well, what will they look like when they relax? Well, they're presumably going to look like blue stragglers. And these objects are on orbits that are quite similar to the S stars. In other words, and I haven't defined what the S stars are. These are the B stars that are in the central arc second, so inside the inner edge of the disk. And that population has a mass function and a kinematics. It's quite different than that you see in the disk. So I think it is interesting to consider the possibility of S stars as blue straggler stars. This is more, the second idea is less clear to me, but I thought I would throw it out there. There's a lot of debate about why we don't see the cusp in the bright giants. The bright giants are the largest giants that are in this population. So is it possible that the giants have been stripped through the action of these binaries? In other words, as binary stars pump up their eccentricity, you might imagine that this could become an effective stripping mechanism. And once they're stripped of the outer envelopes, they're going to become faint. They're just going to sink below our detection limit. And of course, this process may be an important process for thinking about how LIGO sources get generated. And this is an idea that Smadar and others have pursued. Now, binaries are interesting both dynamically, so from the physics perspective for these three reasons, but they're also something to pay a tremendous amount of attention to in terms of our models of the dynamics at the center of the galaxy. The astrometry is easy to get. The imaging cameras are large, and from my perspective, large means tens of arc seconds. To get the spectroscopy, it's very expensive. It's expensive both from the point of view of telescope time and the field of view. So for most of the population, there's only a single RV measurement. So we're very used to the central arcsecond, which has been monitored very carefully. But outside the central arcsecond, we're using 20 years of astrometry, but a single RV measurement. So it's useful to think about how susceptible are those RV measurements to the effects of binaries. And it turns out at beyond an arcsecond, the binaries can play a significant role in altering your radial velocities. So from the disk perspective, this is a project that we've done with Smadar. It's easy to show that, in fact, the disk fraction may be much higher than previously thought. And this is also something to think about in terms of the three-dimensional velocities that have been used to model the dynamics. So in conclusion, let me just say that I think the center of the galaxy is a fascinating place to look at for understanding the dynamics of galactic nuclei. But it is super important to realize that we are only seeing the tip of the iceberg. In terms of what's spectroscopically identified, you're only getting down to roughly 10 times the mass of the sun for the young stars. And of course, you're seeing a very different population for the old star. And with that, let me conclude that over the last 20 years, I think we've gotten great evidence for the existence of a supermassive black hole, and this ability to measure orbits is providing us with a wonderful laboratory for understanding the physics and astrophysics of galactic nuclei. Thanks.